Hey everyone, welcome to today's Explainer. We are unpacking a truly massive shift that's happening right now in chemical research and industrial production. Today, we're looking closely at the chemistry AI landscape as it stands in 2026. We're going to categorize the top platforms that are totally transforming how everyone, from academic researchers at the bench right up to industry professionals on the plant floor, do their jobs. Let's dive right in and see how these tools are taking chemical innovation all the way from the lab to the plant. So check out this quote. The question is no longer, will AI work, but which chem AI strategy gives us the competitive edge? I think that really sets the stage perfectly for us. Artificial intelligence in chemistry has completely moved past that hyped-up buzzword phase. In 2026, it is the absolute baseline standard for innovation. If you want to accelerate discovery or optimize a complex chemical process, you aren't sitting around asking if you should use AI, you're figuring out exactly which specific tools to deploy to get ahead. All right, here's our roadmap for today. We'll kick things off with 1, the 2026 chemistry AI boom. Then we'll look at 2, academic and open source tools. 3, data versus physics simulations. 4, enterprise scale-up and production. And finally, 5, the self-driving lab era. It's basically a logical lab-to-plant journey, starting straight from a university student's desktop and scaling all the way up to a fully automated manufacturing facility. Okay, let's jump right into Section 1, the 2026 chemistry AI boom, breaking the trial and error bottleneck. So, chemistry has always been an incredibly data-rich field. We're talking terabytes upon terabytes of complex molecular pathways and reaction variables. For decades, trying to make sense of all that was a massive bottleneck. It relied super heavily on human intuition and, honestly, just a whole lot of trial and error. Fun fact, traditional drug discovery used to take well over a decade just to find a single viable compound. But today, advanced machine learning, deep learning, and generative models have completely shattered that bottleneck. They've transformed 3 major analytical applications. We're using generative molecular design to literally create novel structures from scratch. We have autonomous process optimization, adjusting reaction conditions in real time. And we've automated the spectroscopic interpretation of incredibly complex NMR, IR, and mass spectrometry data. By automating all these routine tasks, AI frees up chemists to do what they do best, focus on high-level, creative strategy. Moving right along to Section 2, academic and open source tools, the foundation of chemical AI. Let's start our journey at the academic benchtop. Now, before we look at the specific tools, we really need to understand what university students and early-stage researchers are actually trying to achieve every day. And that is retrosynthesis. This is the process of mapping out the absolute most efficient synthetic routes, but working backwards from a target molecule. Think of it like trying to build a massive Lego set, but instead of starting with a pile of bricks, you start with a finished model, and the AI instantly maps out the most efficient step-by-step pathway backwards to create it. It used to take immense time and intuition to figure this out. Now, it happens in seconds. And that brings us to a real game changer, IBM RxN. This pioneer cloud-based tool is trained on literally millions of chemical reactions. But what makes this so incredibly vital for the academic space is that it provides a free tier designed specifically for students and educators. It assists university students directly with those complex retrosynthesis planning tasks we just talked about. Having a tool like this available makes it an absolute cornerstone for modern synthetic organic chemistry education. It's like having a GPS for molecules. All right, Section 3, data versus physics simulations, managing the R&D lab. As we transition out of the university and into the corporate R&D lab, scientists face a really distinct choice in how they manage their research platforms. Do you leverage your own vast troves of historical data, or do you rely on highly accurate physics-based modeling? We see a pretty stark contrast in approaches here. On one side, you've got Albert Invent. This platform acts as a collaborative R&D data hub. It doesn't just predict, it actively learns from a company's proprietary historical datasets to guide future experiments and break down silos between research teams. Then, on the flip side, there's Schrödinger. They take this amazing hybrid approach, combining gold standard physics-based simulations and quantum chemistry directly with machine learning. That offers incredibly high accuracy for complex chemical systems. So you've got 2 very different, but equally powerful, strategies depending on your lab's focus. Of course, there are other highly specialized players in this R&D ecosystem that we should definitely categorize. For example, Luna.ai is leading the pack in generative biology and chemistry, using advanced models for the de novo design of novel proteins and small molecules.
Then you have AtomWise, which uses technology inspired by image recognition, specifically convolutional neural networks, to virtually screen literally billions of compounds for drug discovery. And Citrine Informatics, they focus specifically on AI-driven predictive modeling to accelerate the discovery of entirely new sustainable materials.
Which brings us to Section 4, Enterprise Scale-Up and Production, Bridging the Gap to Manufacturing. Now, we are speaking directly to the chemical engineers. Look, it's one thing to make a reaction work in a tiny glass beaker on a lab bench. It is a completely different beast to scale that up to a massive industrial plant without catastrophic and costly failures. Here's where the platform tools really diverge. DeepChem remains the premier open-source library out there. It democratizes AI by fostering a massive community of developers building and training custom academic models. But when it comes to physical manufacturing, you turn to an enterprise suite like ChemCompilot. This is built for the practical, hard-hitting realities of chemical processing, optimizing yield, cost, and safety, all simultaneously during real-time plant scale-up. Let's look exactly at how a platform like ChemCompilot solves these real-world production challenges. It uses AI to dial in the absolute optimal reaction conditions. Think temperature, pressure, the works. It predicts exactly how a bench-scale reaction is going to behave when you move it to a massive pilot reactor. It integrates right into industrial systems for real-time monitoring and control, suggests greener solvents for sustainability, and get this, it even deploys digital twins. Those are customized virtual environments that perfectly replicate physical chemical processes. The whole shebang is entirely focused on keeping industrial plants safe, efficient, and sustainable.
And the best part is, this technology isn't just theoretical. It is driving tangible, real-world impact right now. 2 prime examples: optimizing complex crystallization for massive process scale-ups, and completely innovating the battery recycling industry by modeling efficiency in highly specialized oxygen-free reactors. This is AI actively driving industrial-scale circularity. It's amazing stuff.
All right, our final stop, Section 5, the self-driving lab era. The future of chemical development. We've gone from the academic bench all the way to the industrial plant. Now, all these specialized platforms we've been talking about are converging into the closed-loop system of a self-driving lab. The AI platforms are increasingly being connected directly to physical robotic automation. Think about this flow. The AI designs the experiment, the robotics physically execute it, the AI analyzes the resulting data, and then immediately designs the next iteration based on what it just learned. And this cycle repeats 24 hours a day, 7 days a week, without a single moment of human intervention. It is literally a relentless, nonstop engine of discovery. But, okay, we do have to ground ourselves for a second. This AI boom comes with very real, practical hurdles. The absolute biggest one, data quality. If you feed an AI poor, unstructured data sets, you are going to get highly inaccurate predictions back. Garbage in, garbage out, right? There's also the persistent issue of interpretability. Deep learning models often act as a black box, which makes it really hard for chemists to trust exactly how the AI arrived at a specific conclusion. Overcoming these technical barriers is absolutely the current frontier for AI developers today. So that leaves us with this final big picture thought. As AI completely takes over the routine data crunching, the complex retrosynthesis, and even the autonomous 24/7 lab execution, how will human intuition actually evolve to shape the future of chemistry? The tools are all there. The landscape has fundamentally changed, but it's the chemist's creativity that will ultimately direct these platforms. Think about what your role is going to be in this highly automated world. Thank you so much for joining me today, and I really hope this explainer gave you a clear, exciting look into the incredible 2026 chemistry AI landscape.